Good day, students. Welcome to our another online session for the course Computer Organization. And in this session, we will be discussing about storage, specifically the concept of RAID, and we will see how different levels are implemented in the particular category. And with some examples, we will be discussing about how to compute the parity for different RAID levels. So to start with our discussion, this is chapter number 6 of the book, storage and other IO devices. And in this chapter, basically we are focusing on the storage systems. What are the storage systems that are being used in a computer system, and what are the significance of the storage, and what are the requirements. And with the passage of time, as a consumer point of view, as a user point of view, the storage requirements are increasing day by day. So we require more storage in order to have our programs to be stored, in order to store our content, so that the storage requirements are definitely increasing, as far as the reliability factors are also the key concerns for the performance parameters. So for the single storage compartment system, for example, we've got a one storage device, or the hard disk device that is being connected in our system. What would happen if we've got any sort of fault in our storage system? And then what would happen to the data that is being stored at that disk? So definitely the reliability factor is a key concern, while the motivation for the RAID. So RAID is basically the redundant arrays of inexpensive disks. So we use multiple disks instead of one single large disk to store our data, so that if in any case we've got any sort of fault or some failure, our data can be retrievable, and the reliability factor can be increased in such a way. So instead of using the larger disk, we will be focusing on the smaller disk. Uh, Instead of one large disk. So parallelism improves the performance basically. So instead of doing all the stuff on one disk, we are distributing the stuff on multiple disks, and plus extra disks definitely are for redundant for the data storage. We can store more data in that, or we can use as a backup, so that in case of any sort of failure, we can recover our data. And this configuration basically provides a fault tolerant storage system. So if any of the disk got failed basically, so we can swap that, hot swap that disk, or replace that disk immediately without compromising on the system performance. So this RAID, the concept of RAID is being defined in different levels. The first, the basic primary level is known to be the RAID 0, and that concept basically evolves the concept of stripped arrays. So that was not the actual RAID concept basically. So as we are not using any sort of redundancy in it, so we just strip the data and distribute the data on the multiple disks. So in case if any of the disks got failed, we can retrieve the rest of the data, but it does improve the performance. So the first level, that was the basic level that was introduced, is known to be the RAID 0. The next level is RAID 1, and that introduced the concept of mirroring. For example, we've got a storage device, a hard disk drive here. For example, it has a 1 terabyte capacity. And if we are mirroring that device, we would use another 1 terabyte hard disk drive. That is just the backup for that 1 terabyte. So we just create a mirror image of our primary device. So in that case, if that device got failed, so we've got our backup, so our data is recovered. The major drawback here is that we are compromising on the storage space. So although we've got the 2 terabyte hard disk drive, but only 1 terabyte hard disk drive is only accessible for the user, and the rest of the second drive is not. It's just for the backup. So in the RAID 1 concept, we use the concept of mirroring, and we've got n plus n disks. So we to replicate the data. If we got n disks of the data, so we require n disks to replicate the data as well. So we write the data to both disks and mirror the disk. On one disk failure, we read from the mirror. So that was the concept that was introduced in RAID 1. The next was the RAID 2. That concept introduced the concept of error correcting codes basically. So and that concept was not used in practice. Basically, it's too complex, just a theoretical idea that we would use that. But on later levels, we do introduce some parity and for the error detection, and to see if we can detect the error and later on to correct that error as well. So RAID 2 introduces the concept of error correcting codes, and if we got n disks, so we require e disks for the error correction basically. So we split the data at bit level across n disks and generate e-bit error correcting code. For example, we are using some sort of Hamming code or some other error forward error correcting codes. But that concept is too complex to implement, so this level is not used in practice basically. Now coming to RAID 3. RAID 3 known as the bit interleaved parity. So we've got n disks. For example, we've got, let's assume that we've got 3 disks. Or just for the example, let's assume that we've got 2 disk storage disks, and we would use another disk to store the parity information. That this is for example, these are the data disks 1 and 2, and we've got another disk that is to store the parity of these 2 disks. So what we use, we strip the data across n disks at byte level, and the redundant disk stores the parity. This stores the parity of the data, and we read all the disks in order to access, and we generate new parity whenever we have to update the data. And upon the failure, we used parity to reconstruct the missing data. So it's also not widely used. The RAID 4 and RAID 5 are basically the frequent use categories, but we will see how this parity is generated later on in our discussion, and we would definitely generate the parities here. Coming to RAID 4 introduces the concept of block interleaved parity instead of bit interleaved parity. So we've got the same configuration here, n plus 1 disk, where the data is stripped across n disks at block level, and redundant disk store parity for the group of blocks. So similarly, we would read only the disk holding the required block, and if there is a change in any of the block, we have to compute the parity and update the parity on the parity disk. So upon the failure, we use that parity to reconstruct the missing data. So how the parities are computed? If you see that we've got these blocks D0, D1, D2, and D3 are stored in the disk, and we've got a parity disk here. And if there is any change in the block, for example, this D0 is changed, previous D0, this is the previous D0, this is the updated D0, then what we would do, first of all, we would change D0 here, and then we would reconstruct the parity with the newer data set by exclusive OR operation, and write it to the parity disk. Whereas compared to the RAID level 4, we don't have to access all the disks. We only access that disk that has the change in the data. So we would make the exclusive OR with that. First of all, updating D0 here, then making the exclusive OR that, and we just simply have to make the exclusive OR with the previous parity that has been stored in order to generate the new parity. So this is the difference that how we're going to compute the parity for RAID 3 and RAID 4. Now coming to the RAID 5, that is the distributed parity. So instead of storing the parity on a single disk, we distribute the parity here. So in the previous case, first, what if the parity disk got failed? So we don't have any other mechanism to ensure that the data is reliable or not. So instead of storing the parity on a single disk, we just distribute the parity on different disks. So that the parity disk being a bottleneck can be avoided. So but the parity is being distributed here instead of on a single disk, which you can see that on a RAID 4 all the block parities are stored on a single disk, and if this disk parity disk got failed, then we don't have any mechanism to recover data or to ensure that the data is reliable or not. But if the data is distributed here, then the performance factor or the reliability factor is much more increased as compared to the RAID level 4. Now coming to the last level, that is RAID 6, and it's a multi-level parity. Basically, we use P plus Q redundancy basically. So we've got n data disks and 2 disks to store P and Q parity basically. So we compute the parity in rows and columns basically. For each disk we compute the parity, and for multiple disks at the same location of the blocks, other different blocks, we also compute the parity. So like RAID 5, we got two set of parities basically, and it's greater fault tolerance to more redundancy basically. So this system is much more advanced and in use basically. So RAID can improve performance and availability, and high performance requires hot swapping and assuming independent disk failures. So it's too bad if the building burns down basically. So see hard disk performance, quality, and reliability factors. We can go into detail by visiting this website. We can go and check out what are the performance factors and quality for the reliability and quality. If anybody is interested in studying those, just go to the link and you will find out different sets of parameters that are used to indicate the performance of the system. Well, that was all for this session. Inshallah, we will meet again, and we will see some dedicated topics regarding the prefetches and the multiprocessing systems.